Welcome to our YouTube channel விடியற்காலை விண்மீன் NEET 2022 Physics Few Solved Question and Answers. Before moving on to the video, please subscribe, comment and share. The dimensions m, l, t power minus 2, a power minus 2 belongs to the 1. Self-inductance, 2. Magnetic permeability, 3. Electric permittivity, 4. Magnetic flux. Force SI unit is kg meter per second square and its dimension is m, l, t power minus 2. kg is equal to m equal to L, S square is equal to T square. Now writing the equation for magnetic permeability, we get 2 pi times force times distance divided by current square times length. So this is the formula for magnetic permeability. Substituting the dimension for force, we get ml t power minus 2 and the dimension for distance is L, dimension for current is A, dimension for length is L. Now cancelling the common terms, we get the final answer for the magnetic permeability is m l t power minus 2 a power minus 2. So the right answer is option 2, magnetic permeability. The angular speed of a flywheel moving with uniform angular acceleration changes from 1200 rpm to 3120 rpm in 16 seconds. The angular acceleration in radian per second square is 1. 4 pi, option 2. 12 pi, option 3. 104 pi, option 4. 2 pi. The angular acceleration is given in the formula as omega f minus omega I divided by t, that is rate of change of angular speed d omega by dt. d omega is omega f, that is the final angular speed, minus the initial angular speed omega I in just 16 seconds. Omega f is given as 3120 rpm. Omega I, that is the initial angular speed, is given as 1200 in 16 seconds. So substituting the values, we get 1920 divided by 16 rpm per seconds. Now cancelling, we get 120 times 2 pi by 60, which gives 240 pi divided by 60. And the final answer will be 4 pi radian per seconds. Here we are having 1920 rpm per second. This is converted into radian per second by multiplying 2 pi by 60, and the final answer we get 4 pi by 4 pi radian per second. So the correct answer is option number 1, 4 pi. Next question. A copper wire of length 10 meter and radius 10 power minus 2 divided by root pi meter has electrical resistance of 10 ohm. The current density in the wire for an electric field strength of 10 volt per meter is option A 10 power 6 ampere per meter square, option 2 10 power 5 ampere per meter square, option 3 10 power 5 ampere per meter square, option 4 10 power 4 ampere per meter square. Before solving, let's write the given data. L is equal to 10 meter, R is given as 10 power minus 2 divided by root pi meter, and the resistance is given as 10 ohm. Electric field strength E is given as 10 volt per minute. Now the formula for the current density J is equal to sigma E, where sigma is the conductivity, E is the field strength, R equal to rho L by A. This is the formula we know. In this, from this, rho is found as RA divided by L. Here, the conductivity is inversely proportional to the resistivity. Sigma is inversely proportional to the resistivity. So, substituting in the current density, we get LE divided by RA, and substitute the values of L, E and A. We get J equal to 10 into 10 divided by 10 into pi into 10 power minus 2 divided by root pi the whole square. Here we are finding the area. So this is the area of the circle. So pi r square is the formula. R is given. So substituting, we get 10 into 10 power minus 4, which gives 10 power 5 ampere per meter square. So this is the answer for the question. So the right answer is 10 power 5 ampere per meter square. Option number 3. That is the right answer. The graph which shows the variation of de Broglie wavelength lambda of a particle and its associated momentum is, the four graphs are given. It's a relationship between the lambda and the momentum. Wavelength and the momentum are given in four pictures. Before solving, let's write the relationship equation for wavelength and the momentum rho. Lambda is equal to h by rho, where h is the constant. Hence, lambda is directly proportional to 1 by the momentum. In lambda is inversely proportional to the momentum. That is the meaning of this equation. Sorry, I'm sorry for that. Lambda is inversely proportional to the momentum, or momentum is inversely proportional to the wavelength. When the momentum becomes zero, wavelength becomes infinity. When the wavelength becomes zero, momentum becomes infinity. So with the help of this relationship, we can able to find the correct answer. We can eliminate option 3 and option 4. We can eliminate because they have the finite value. Because this graph starts from 0, it is a finite value. Here too we have the finite value. Anyway, this line will touch both x-axis as well as the y-axis, so it is finite. We have only two options, option number 2 and option number 1. Here, according to the relationship, lambda is inversely proportional to the momentum. When momentum becomes zero, wavelength goes to infinity. Momentum becomes zero, wavelength also becomes zero in the option 1. So we can cancel out the option 1. So what is remaining? Option 2 is remaining. So here too we can check the other relationship. When the lambda becomes 0, that is wavelength becomes 0, the momentum should go to infinity. Wavelength is in the y-axis, momentum is in the x-axis. When the momentum becomes 0, yes, obviously when the wavelength becomes 0, the momentum goes to infinity. So the right answer for this question is option number 2. A series of LCR circuit with inductance 10 Henry, capacitance 10 microfarad, resistance 50 ohm is connected to an AC source of voltage V is equal to 200 sin 100t volts. If the resonant frequency of an LCR circuit is V0 and the frequency of an AC source is V, then V option 1 V not equal to 50 by pi hertz, V is equal to 50 hertz. Option 2 V is equal to 100 hertz, V naught is equal to 100 by pi hertz. Option 3 V naught equal to V equal to 50 hertz. Option 4 V naught equal to V equal to 50 by pi hertz. Let's move on to the solution for the question. At resonant frequency, XL is equal to XC. This is a relationship. We know inductive reactance is equal to capacitive reactance at the resonant condition. XL equal to omega L. XC is equal to 1 by omega C. From this, we found omega square is equal to 1 by LC and omega is equal to 2 pi Fr, where Fr is the resonant frequency. Substituting the values, we get 4 pi square Fr square is equal to 1 by Lc. So F square is calculated as 1 by 4 pi square Lc. From this, Fr is equal to 1 by 2 pi square root of Lc. Now we have the data. L is equal to 10 Henry, capacitance value C equal to 10 microfarad. Substituting the values of L and C in the resonant frequency formula, we get 1 by 2 pi square root of L is 10 Henry, C is 10 microfarad. So 10 into 10 to the power minus 6. Simplifying, we get 1 by 2 pi square root of 10 to the power minus 4. Further simplifying, we get 100 by 2 pi, which gives the resonant frequency V0 equal to Fr equal to 50 divided by pi hertz. So we arrived the conclusion that the resonant frequency of the LCR circuit is 50 by pi hertz. So the option number 4 is the right answer. Now, here is the logic circuit. The truth table for the given logic circuit is, before moving on to the option, let us derive the equation. Here is the input A. Here is input B. Now, this is the NAND gate. This is the NOT gate. And here is the AND gate. You should know about the NAND, NOT and AND gates so that it is easy to understand it is easy to solve the question. Now, the inputs of two NAND gates, here it is A, here it is B, whereas the second NAND gate input is A bar and B. At the output of this NAND gate, we get A dot B bar. A dot B bar. This is the output of the first NAND gate. The second NAND gate, at the input, we have A bar and B. It is at the output, we get A bar dot B, the whole bar. This is the output of the second NAND gate. Now, the two outputs of the NAND gates are ANDed and we get the output, final output C. So C is equal to A dot B the whole bar dot A bar dot B the whole bar. So here is the output C. Using this output, we are going to find the answer for the given logic circuit or the truth table for the given logic circuit. Let's move on. When A when A is equal to B is equal to 0, both inputs are 0. What is the output? Let us check. A and B both are 0. We get output C as 1. How do we get? Because here you can see 0 dots. Here if you substitute A and B are 0, we get 0 dot 0 the whole bar. We get 0 bar, that is 1. Another one, 0 bar dot 0, that is 1 dot 0 the whole bar, that is 0 bar. Again we get 1. So 1 dot 1, we get C as 1. That is the output. For when the input becomes 0 0, we get the output 1. So look at the truth table for the given logic circuit. Option A, when both inputs are 0, C is 1. So we have both inputs are 0, C is 1, right? Now if you look at the option 2 and 3, when A is 0, B is 0, we get C also 0. Option number 3, when A is equal to 0, B is equal to 0, option C, sorry, output C is also 0. So we can eliminate option 2 and 3. Why? Because when both inputs are 0, we should get output C is equal to 1. So C is equal to 1 in the option 1 as well as option 4. Now the truth table will be either option 1 or option 4. How to find out the correct answer for this question? Now when A is equal to 1, B is equal to 0, substitute the value in the C output equation C. We get C is equal to 1 dot 0 the whole bar dot 0 dot 0 the whole bar. So the C will be 1. C is 1. Check the options 1 and option 4. When inputs are 1 0 1 0 1 0, output should be 1. Here in the fourth option, both if A is 1, B is equal to 0, C becomes 0. So this is wrong. So we can eliminate the option number 4. Already we have eliminated option 2 and option 3 because when both inputs are 0, we should get output C is equal to 1, whereas in option 2 and 3 we are getting output as 0. So this is wrong. Similarly, as well as the option number 2 also wrong. So our final answer for this question is option 1. A Wheatstone bridge is used to determine the value of unknown resistance X by adjusting the variable resistance Y as shown in figure. For the most precise measurement of X, the resistances of P and Q. Here is the picture and the options are should be approximately equal to should be approximately equal and or small. Option 1. Option 2 should be very large and unequal. Option 3 do not play any significant role. Option 4 should be approximately equal to 2x. This is the Wheatstone bridge. When the bridge is balanced, current flowing through the galvanometer is zero. There is no current will be flowing, that is zero current. Current will be zero at the balanced condition. So writing the equation for at the balanced condition, we get P by Q is equal to X by Y. When X is equal to Y, we get P by Q is equal to 1. That is, P is equal to Q. So, the right answer for this question is should be approximately equal and or small. This is the right answer for the question. Two resistors of resistance 100 ohm and 200 ohm are connected in parallel in an electrical circuit. The ratio of thermal energy developed in 100 ohm to that in 200 ohm in a given time. Option 1, 1 is to 4. Option 2, 4 is to 1. Option 3, 1 is to 2. Option 4, 2 is to 1. Before solving, let's draw the circuit. Two resistors R1 and R2 are connected parallel with the source, voltage source. Now, instead of finding the ratio of thermal energy, developed across 100 ohm and 200 ohm, we are going to find the power across the each resistors. The formula for power is equal to V square by R1. Power 2 V square by R2. R1 is given as 100 ohm, R2 is given as 200 ohm. Now taking the ratio between P1 and to the P2, we get P1 by P2, V square by R1 divided by V square by R2, that gives R2 by R1. Substituting the values, we get 200 divided by 100. So the power ratios P1 is to P2 is equal to 2 is to 1. So the correct answer for the question is option 4, 2 is to 1. Next question. As the temperature increases, the electrical resistance. As the temperature increases, the electrical resistance. Option 1 decreases for both conductors and semiconductors. Option 2 increases for conductors but decreases for semiconductors. Option 3 decreases for conductors but increases for semiconductors. Option 4 increases for both conductors and semiconductors. Here we are going to use the property of conductors and semiconductor. In conductors, when the temperature rises, resistivity also increases. When the temperature rises in conductor, resistivity also rises in the conductor. As a result, the resistance increases. Whereas in semiconductor, when the temperature increases, resistivity decreases. This is the property of a semiconductor. When the temperature increases, resistivity decreases and the resistance is also decreasing. With the help of this property, we are going to select the right answer. That is option number 2, increases for conductors but decreases for semiconductor. That is the right answer. Now, moving on to the next question. If a soap bubble expands, the pressure inside the bubble 1 remains the same, number 2 is equal to the atmospheric pressure, number 3 decreases, number 4 increases. Now, when the bubble has the radius r1, inside the bubble, let us assume the pressure is P1. When the extra air enters the bubble, the bubble radius will be bigger. It has the radius r2 and inside the bubble the pressure is P2 because extra air enters into the bubble. Now comparing these two pictures, R1 is definitely lesser than R2 because extra air enters, that makes the bubble to expand, that is R2 will become higher than R1. Extra air increases bubble radius, that is bubble expands, decreases the pressure inside the bubble. So when the radius increases, pressure inside the bubble decreases. With this, we can able to give the answer. If a soap bubble expands, the pressure inside the bubble obviously decreases. Option number 3. That's all the video. Thanks for watching. Please watch other videos in our channel. Don't forget to subscribe our channel at Vidyar Kale Winmin. We will see in the next video. Until then, it's goodbye from Vidyar Kale Winmin. Thank you one and all.